right, well, welcome. What we have here is we're going to go through a little tutorial on how to work with the definite integral. If you watch some other tutorials from either me or some others, you might understand that Riemann sums are calculating the sums of rectangles. Um, and what we have is we have this equation, and for a Riemann sum, we understand that when we have this part is the height of our rectangles that we're calculating. All right, and we know that this right here, this is our width of our rectangles that we're calculating. And we multiply these together, what we get is the area of our rectangles. And a Riemann sum is calculating the area, all right, of a rectangle, all right, of a rectangle. And we're going to add in a bunch of these rectangles underneath the curve of f of x, and that will give us our area, which is actually what we find, since it's stating find the area on the curve. But now, what a Riemann sum is in order to find what's called a definite integral is that we're going to take the partitions, the number of rectangles we have. We're going to say that length of the partition, all right, or essentially the width, is going to be approaching 0. Now, when that occurs, what happens is that the area underneath the curve, and I just draw like a little curve right here, and this is like a little exponential function right here. When we find these areas of the rectangles, and we go from A to B, okay, from A to B, what we have then, if I draw this and I'll go like this, and it doesn't matter where you go, but whatever number of partitions you have, and this is right now a Riemann sum, which we call a right Riemann sum, all right? And we go down like that. We find these areas, but what happens when the width, this delta x, all right, or our p-value, oops, that should be p, all right, that approaches 0. So if this width gets infinitely small, all right, or if you think about it, what happens if we have a infinite number of partitions? Well, what happens is that these rectangles get very, very skinny. And what happens when they get really, really skinny is that we now just begin to just take the heights and we're just simply just adding up all the heights together. And what we have is what's referred to as a definite integral, in which we are finding the actual area underneath the curve. All right, and that is what a Riemann sum is using rectangles where our rectangles, that area gets infinitely small. All right, so this is the notation, or two different ways of notating how you find what's known as a definite integral. And we write a definite integral this way. And I like this notation because I think it's easier to understand when your partitions become really, really numerous from A to B. All right, you have delta x, which approaches 0, and then you have a Riemann sum, or a definite integral. Now, a definite integral, there is no more estimating. We don't need to have a right rectangular or left rectangular, midpoint rectangular approximations, or even Simpson's rule or the trapezoidal rule, because now what we can do is we can use this, okay? And here is a notation for a definite integral. We have the Roman sigma. We have our lower limit, which is a, to upper limit b. We have our f of x, which is our heights, which is known as our integrand. And we have our variable of integration, which is known as dx, which actually represents, all right, delta x, which is referred to as a dummy variable, because essentially this doesn't have any bearing whatsoever on our calculations. All right, because we know those are 0. So how do we find definite integrals? Well, to help us understand this, all right, is to help us understand how to find integrals and how they work, how we can have different areas and how these areas work, is I'm going to think about when you find, all right, the integral, all right, of a velocity function. I've talked about this before, but when you find the integral of velocity, all right, now what we get, all right, from A to B, all right, actually I want to go from A to B. We'll just say we're going to do the integral. Well, what happens is that we're breaking down, all right, and we're finding the area underneath a velocity function. And so what happens, if we have a velocity, let's just say I have just a simple velocity, this is v of t, and I find the area under this, and this is going to be my time, all right, and we'll say that our velocity is in meters per second, all right, and we'll say our time is in seconds. And if I would find the area underneath this curve, essentially, what do I get? Well, to find the area, I'm going to take velocity times time, and that gives us, all right, what we refer to as our distance. Our distance. Now, this distance we usually refer to as s, okay? It would be s, all right? So the integral from s to let's say just we go from 0 to an x right here. What we'll get is s of x right there, and we would have our velocity function. Or sorry, we would have our distance time function. So this what we get is distance. Now, sometimes we get distance because when you take an integral, you're either taking the integral of speed or you're taking the integral of velocity to get this distance function. And this will help us understand what we're going to be talking about next is, do we have negative integrals? Or sorry, do we have negative areas? Well, when you talk about speed, all right, is the absolute value of the velocity function. All right, speed is the absolute value of the velocity function. Velocity, all right, is basically a vector with direction, right? Or it's a size with direction, right? Size with direction. So speed or velocity, we have direction. All right. If our velocity is greater than 0, moving to the right, correct? If our velocity is less than 0, we're moving it to the left. So it has direction. The absolute value velocity or speed is when everything is positive. So everything is above, so everything moves to the right, or we don't contemplate distance or direction, as that's what we have. Now, with that way of thinking, this can totally make sense when we talk about total distance versus net distance. Total distance versus net distance. For example, if I had a velocity graph, all right, which was x squared minus 1, all right, so we have this right here. X squared minus 1, and we'll say for all x values greater than 0, and we'll put that in there. If I have this, all right, I have this graph right here. Now, looking at this, we want to find what is the distance it takes to go from, let's go from A to B, all right, A to B. So here's A and here's B. Now, when we do this, when we take this integral, all right, we're going to find the area underneath this curve. Well, if you look at this area, notice that this area is below the x-axis. Then we go to B, all right, where this intersection is, which is 1. We go above, we're finding this area right here. Well, in this case, we'll be adding the area below the x-axis with the area above. Well, what happens when you have an area below? Well, the area below is going to be negative, and the area above the x-axis is going to be positive. And right here, if you add a negative area plus a positive area, what you'll refer to as net distance or displacement. Displacement includes the negative area and the positive area. That is net distance, or we refer to as displacement. Total distance is where we don't take into account the negative. We're looking for how far we totally traveled. So in order to figure this one out, we need to take this part right here, and we're going to take the absolute value of the velocity function, or the absolute value of the function itself, find the total area. So sometimes this is total distance or total area. All right, total area. And what we're going to do is we can have to rearrange this, but what we create then is the same area, but now this is going to be above the x-axis, and we have this right here, which is also above. And now we have a positive area plus another positive area, and that's what's going to give us our total area or total distance traveled. Hopefully that kind of makes sense a little bit, okay? So what we just discussed right here is how we can use a definite integral and how this definite integral and how we can use it to find the areas. I'm going to stop here, and I'm going to get into some problems on showing you how we can find and solve these different areas using a definite integral in the next tutorial.